Hi, in this lesson we're going to render some volumes. I've emitted some dust from the falling pieces of rubble from our earlier lessons, and we're going to look at how to render it efficiently. Here's the dust sim, and I'll show you a flipbook of that with the rubble and the particles. I've already cached this volume, but just before we move on to rendering it, I just want to draw your attention to an optimization that is really worth knowing about. I'm importing density and velocity from my .NET. This is a fairly simple dust sim, so we're not going to get fancy with anything else. And there's a volume visualization, which looks like this. That's just tweaking the density and that kind of thing so that we can see it properly. And then after that, there's a node called volume compress. This is an extremely useful node for optimizing volume renders. What it does is it takes the fields of a volume and it can dramatically reduce their size without really having any impact on how it renders. If we go through the settings in here, the first thing is update compression settings should be on. So this makes the node recompress the volume. And then there's a constant tile tolerance and a quantization tolerance. So the first one looks for tiles that are all the same value. Well, it looks for areas of tiles that are all the same value, and then it's able to represent those by one number, by one value. So that's one optimization. And then the other one is quantization. Quantization essentially quantizes the values, so it replaces a continuous floating point value with steps, which are more easily compressed. And then dithering essentially gets back some of the detail that you lose with that. But with both of these, you can actually use quite small values and it will have a fairly big difference on size. Then there is U16 Bit Float. This uses, as it says, the 16-bit float rather than the full 32-bit float resolution to store your values. And then lastly, I have a volume blur node, which is blurring the density volume. I'll just show that. And then we're using that as a mask inside our volume compress. So we're just grabbing it there, name equals density. And what we're doing is we're setting any voxels that are outside this slightly blurred out volume to 0. And that makes them obviously very easy to compress. Any voxels that contain density of greater than 0.01 will be not masked. And any that have densities lower than that will be masked. If we compare the RAM consumption before and after the volume compressed node, we're looking at, I'll just pin that. So we're looking at 83.78 megabytes, and then for that frame. And then for this one, we're looking at 16.26 megabytes. For something that looks and will render pretty much identically, that's a pretty dramatic saving in RAM. And obviously that translates into disk space usage as well, and how long the volume will take to load into the renderer and how much memory it will consume when it's being rendered. So I would strongly recommend always using a volume compress when you're working with native Houdini volumes. Then it's being cached out, it's being read back in from the cache, and we can get to rendering it. Okay, we're back up at the object level, so let's drop down a geometry node, which we will call render underscore dust to keep it consistent. And we'll turn off the display flag for now. We'll jump inside and we'll create the usual object merge, which we will point towards the output of our dust sim. I'll call that merge volume. and create a null called render. And then we'll drop down a material node because we're going to want a material to render this with. Okay, so let's go to the material palette, and I'm going to create a basic smoke. It's a nice simple volume shader, doesn't have too many bells and whistles, but for something like dust it's perfect. So we'll just drop that into our matnet. There it is. We'll jump in there, and we'll just call that dust. And we'll pop it up here so it's nicely arranged. And then we'll just attach it in here. Okay, now that that's hooked up, let's do some rendering. When we're rendering anything transparent like dust, it's very useful to be able to render against a backplate. So I'm going to load one here. I'm just going to grab our previous render of the rubble and the particles. I'm going to hit accept. So there it is, that's loaded in as a backplate. And now if we render our dust, we can get a good idea of how the dust looks against the same image that we'll be rendering it with. Now if I turn this off, you can see that the dust actually looks quite dense, but that's actually a false impression. When you render something quite transparent like particles or dust against a black background, they can look much denser than they actually are. So if you look at the alpha, that looks fine. But then when we see it against the backplate, it's actually quite light. Now that that's rendered, we can go and start adjusting our materials. So we'll just go to our matnet, and the first thing we want to do is change the color of our dust. It probably shouldn't be white because it's falling with some pieces of rubble and some brownish colored particles, so let's make it a brownish color. Probably a bit less saturated than that. Okay, I'm pretty happy with the color, so we can change the density. We want to maybe go a little bit denser, but not too dense. And we'll see how it looks out towards the edge where it's a little bit more wispy. Okay, I think that's pretty cool. There are various other things that we can tweak on the shader, but I think that for what we're doing here, this is probably fine. The next thing we should do is enable motion blur. Now, volumes are actually the only type of geometry in Houdini that I would render with velocity blur by choice. They're nice and soft, and it's kind of hard to read exactly where the contact point with other geometry would be, so they're quite forgiving in terms of motion blur, and really velocity is just the most practical way to do it. So let's go and enable that. So if we go to the render tab on our dust object, let's just turn on velocity blur and hit allow motion blur. or shutter offset is 0. And I'm actually just going to hide the background for this because it's much easier to see motion blur on fairly wispy volumes when we're not looking at the background. Okay, well that seems to have worked pretty well. If we compare it to the previous render, we've got some nice blur going on. The next topic I want to look at is optimizing volume renders. Now that we've added motion blur, this has got a little bit slower than it was before, so there are some good techniques we can use to make that go faster. Right, I'll just set our exposure back to 1, and I'll just clear that marquee. Something I really like to do when I'm optimizing renders is to set the resolution much lower. If we go down to a quarter resolution, it means that the baseline time that our render takes is going to be pretty quick. And that's much better than waiting for an hour to find out how long your renders take before you start optimizing. So we'll render that and we'll keep an eye on the time up here. Okay, so that took 46 seconds. Now the first thing to look at is pixel samples. They're actually pretty low here. We could maybe go slightly lower. I think 3x3 is a pretty good starting point, but 2x2 will be a little bit quicker. Okay, so that's less than half the render time, so we're at 20 seconds now. But it's got a little bit noisy. Now, when we're rendering volumes, there is a setting called Stochastic Transparency, which is a form of anti-aliasing that's designed specifically for transparent things like volumes. So we can actually crank this up quite high without it taking an excessively long time. So let's try setting that to 16 and see what we get. So you can already see this is quite a lot smoother. Okay, so that was over a minute, so that's maybe a little bit too high. Let's set that back to 8. Okay, that's better. That's, I would say, similar to our original render, but it's only taken 37 seconds rather than 47, so that's a significant improvement. So the next thing I want to look at is volume step rate. This determines how frequently the ray fired from the camera through the volume samples the voxels. Here's a diagram of a camera firing a ray through a volume. The blue grid represents the voxel grid, and each of the ticks on the ray, which I'm indicating here, is a sample point. In this example, we're seeing a sample every 2 voxels. So there's one, there's a voxel, there's another one, there's a voxel, and so on. So this equates to a volume step rate of 0.5. So we're skipping every other voxel. This volume doesn't have much density, so the ray travels right through and we'd see objects on the other side. So if there's something here, that would be visible to the camera. In this slide, we're seeing a volume that is much denser on the lower half. And a ray traveling through a volume this dense doesn't get far before it's extinguished by the density. And because it's sampling the volume that takes time, we have far fewer samples here, and that means that this will render much faster for the same volume step rate. And that means that if we're rendering a volume that is very dense, we can actually afford to raise the volume step rate significantly in order to resolve detail around that sort of first little bit of the volume that we're sampling. And this works really well for things like thick smoke or pyroclastic flows, where the ray doesn't ever get very far into the volume, but that little depth that it does travel, we want to be able to resolve very clearly and crisply. Conversely, we can speed up the rendering of wispy low density volumes by dropping the step rate, and you can see that here in the upper ray. So we're now sampling every fourth voxel, so this is 0.25, which is actually the default in Mantra. And you think that would be a problem, sampling this sparsely, but actually with a wispy volume like this, there's so little detail visible that you can actually get away with quite sparse sampling. Lastly on this topic, don't forget that the volume step rate isn't based on world units, it's based on the resolution of the volume. So this volume is being rendered with a step rate of 0.5 every other voxel, but so is this one. So it's worth bearing in mind that if you change the resolution of your volume, you really need to make sure that you have an appropriate volume step rate. Otherwise, you can easily under or over sample your volume, and that can lead to either very slow renders, or conversely, it can lead to very fast renders, but without much detail. So something to keep an eye on. So let's set this to half what it was, to 0.125. Okay, so that's 33 seconds. And let's go to half again. Let's go to 0.06. Okay, 25 seconds. So that's approximately half what our original render was. It's maybe a little bit noisy, but we can probably clean that up by just increasing the stochastic sample slightly. And I would say that that's a significant improvement. We can also look at the volume shadow step rate, which is essentially a multiplier on the volume step rate. When shadow rays are fired from the sample points in the voxels towards the lights, they're sampled at this multiple of this rate. So generally I wouldn't change this very much because we're already sampling it quite sparsely, but it's always worth looking at. Okay, I'm going to set the resolution back to the half resolution we originally had it at, and we'll just see how long that takes to render. Now this might seem like it's a little bit noisy, but you've got to remember that we're rendering this against a background that looks like this, and also we're rendering a kind of dusty, gritty volume, so a little bit of noise in there isn't necessarily a bad thing. Okay, I think that works pretty well. We could probably actually get away with lowering the quality a bit more because it's so transparent. But I think we'll leave it there for now. Here's our rendered dust comp with holdouts from the rubble and the falling particles. Notice that the motion blur trails from the falling particles are quite noisy, so that's something that would probably be good to clean up in a future version. And here's how our dust looks composited on top of the render we did previously of the rubble and the particles. And that's the end of our volume rendering lesson. In this lesson we learned how to compress volume caches, how to render volumes with motion blur, and how to optimize our volume renders so that they go a little bit faster. I'll see you in the next lesson.